You know, we use proofs all the time, right? Proving your point in an argument with a friend, a mathematician proving some complex theorem, a lawyer proving a case in court. But have you ever, really stopped to ask, what is a proof? At its core, not a specific proof, but the very essence of one. What's the perfect shape of a logical argument? Well, that's the rabbit hole we are jumping down today.
So here's how we're going to do this. We're going to peel this topic back like an onion. First, we'll tackle what we even think a proof is. Then we'll dig into what gives a proof its power. After that, we hit a really tricky question. When are two proofs actually the same? From there, we'll see how logic kind of creates its own meaning from within. And finally, we get to the core, the massive quest to unify all of logic into one grand theory. All right, first up, the real meaning of proof. I want you to forget your high school geometry class for just a minute. We are thinking way, way bigger. We're on a hunt for the universal blueprint, the thing that underpins all logical reasoning everywhere. I mean, it seems obvious, doesn't it? A proof is just a series of steps that leads to a conclusion. But general proof theory really challenges that simple idea. It asks us to forget the specific rules for a second and think about the very nature of justification itself. What are the absolute rock-bottom requirements for any valid argument in any system you can possibly imagine? And this, right here, is our key. General proof theory, or GPT, isn't just another flavor of logic. Think of it as the study of the engine underneath all logics. It's trying to find the universal principles that are true for classical logic, for intuitionistic logic, for any system you could dream up. It's about the deep structure of reasoning itself. Okay, so if we're looking for a blueprint for proof, what actually gives that proof its power? That brings us to section 2. If proof theory is the study of logic's engine, this next question is all about what makes that engine actually turn over and go. The legendary logician Dag Prawitz just nailed this central question perfectly. See, it's not enough for a proof to just be a list of steps. Something has to give it its punch, its justifying force. Why does a correct proof actually force us to accept its conclusion? Where does that authority, that epistemic power really come from? So how did Prawitz even begin to tackle this? Well, he laid out this 3-step plan. First, he said we have to stop thinking so narrowly and look beyond our traditional systems. Second, we need a theory that explains how a proof actually creates knowledge or justification. And third, he developed this killer concept of grounds. Now, put simply, your grounds are just the evidence you already have. So a valid inference is just a legitimate, rock-solid rule for moving from the grounds you have to a new conclusion, creating new, justified grounds as you go. And now for a really fun and surprisingly deep puzzle. This sounds like such a simple question, but it is one of the biggest problems in this whole field. When are two proofs that look totally different actually the same proof? Let's try an analogy. Okay, say you and I both bake a perfect chocolate cake. My recipe had 10 steps, your recipe had 15 steps, but at the end of the day, they produce the exact same, identical, delicious cake. Are those two recipes fundamentally the same? Well, this is the identity crisis for proofs. If two different sets of logical steps get you to the same conclusion, are they just two different roads to the same place, or are they different proofs entirely? Logicians have come up with two main ways to solve this. Prawitz's idea is all about simplification. You take two proofs and you just chop away all the unnecessary roundabout steps until you're left with the most direct path, the normal form. If those normal forms match, the proofs are the same. Lambeck's approach is the opposite. It's about generalization. You look at the proofs through a telescope, zooming way out to see their most abstract structure. If they look identical from that bird's eye view, they're the same proof. Okay, next layer of the onion. Where do words like and, or, and if then actually get their meaning? Is and meaningful because of how we use it in the real world, or is its meaning defined purely by the rules of logic itself? Welcome to the wild world of proof-theoretic semantics. The absolute key concept here is something called harmony. The best way to think about it is like a lock and a key. An introduction rule tells you how to build a logical statement. That's like forging the lock. For instance, if you have A and you have B, you can introduce A and B. Simple enough. The elimination rule then tells you how to use that statement. That's the key. So if you have A and B, you can get A back out. A logical system is in harmony when every lock has a key that fits it perfectly, and every key opens its one specific lock. No more, no less. It has to be balanced. And there are two main ways logicians check for this harmony. Reductive analysis is kind of like being a mechanic. You get a weird, complex new part, and you explain it by breaking it down into the standard parts you already know, like and or if-then. Foundational analysis, on the other hand, is more like being an engineer. You create a single, universal blueprint that explains how any part, old or new, should work within the whole system. So, if we have rules for creating these well-behaved, harmonious logical systems, can we take it one step farther? This brings us to our final and by far most ambitious destination, the attempt to build a single framework that can unify all of them. Now, to even attempt to build this grand unified theory, logicians have developed some seriously powerful frameworks. We're not going to get lost in the weeds, but we are going to touch on a few of the big ideas here. One that expands what a proof even is, one that's like a diplomat between different logics, and one that, well, it turns proofs into something else entirely.
Let's start with bilateralism, because this one really stretches your brain. See, traditional logic is all about assertion, proving something is true. Bilateralism makes this radical claim that denial, proving something is explicitly false, is an equally fundamental separate act. So it creates a system with two kinds of derivations, regular old proofs, and these things called dual proofs for denial. It's a huge step toward an even deeper theory of reasoning, one that treats yes and no as equal partners from the get-go. Then you've got ecumenical logic. Think of this one as a diplomatic space, like a United Nations for logic. You've got different systems, like classical logic and intuitionistic logic, that actually disagree on some fundamental principles. Ecumenical logic doesn't try to pick a winner. Instead, it creates this shared framework where both can operate by their own rules side by side. It lets us see exactly where they agree and where they differ, letting them coexist peacefully. And finally, we get to the most abstract of them all, categorical proof theory. With this approach, you stop thinking about proofs as a list of sentences. Instead, a proof becomes a mathematical object in its own right. It's an arrow that takes you from your starting points, your premises, to your conclusion. This completely reframes the study of logic, moving it into a new and powerful mathematical world. And it reveals these incredibly deep structural connections between systems that look totally different on the surface. So wow, we've gone from the simple question, what is a proof, all the way to these incredibly abstract frameworks that are trying to unify all of logic. Which leaves us with one last massive question to chew on. If logicians actually pull this off, if they create a truly unified theory of proof, what have they actually found? Is it just a cool, formal mathematical game? Or have they uncovered the fundamental grammar of all rational thought, the very shape of reason itself?